start with this problem. You let me know if we already did that, then we can continue and skip this one. But so this problem is continuing, and now what we have done is we have actually put the value of the bequest. So now the value of the bequest is B, and we have the same problem, and we would like WT, which is the bequest left for charity or children or whatever, to be bigger than or equal to 0. Now let's see the problem that we solved. Yeah, first let's apply the principle. So assume that T denotes the time of the individual's death, and that is the bequest value. B is bigger than B0, and WT is the wealth left for his heir. So the Hamiltonian is standard. We have log C lambda times RW minus C. Lambda dot is standard. Transversality condition now are lambda T is bigger than B, and lambda T minus B times W star T equal to 0. That sort of tells you, how clearly, if B is very large, that means the person puts a whole lot of value to leaving the wealth to his heir, then WT will become larger. So as B increases, more and more wealth will be left. That is understood. It's also possible, and we already know when B equal to 0, no wealth will be left because there is no reason to leave any wealth if there is no value of leaving wealth. The idea then is to consume the wealth all the way to 0. Leave 0 wealth. But of course, the consumption cannot be more than leaving 0 wealth, because if you consume more than 0 wealth, then wealth will become negative, and you are not only becoming bankrupt, but you are owing to the society before you die, and that's not allowed. Okay, so let's go to the problem where we solve this. Remember here, we left B0 is a constant here, but we like to leave that as a B0 because we are trying to connect this to the next problem, and this is the bequest. So there may be a bequest function, okay? And that bequest function has a value 0 at 0 wealth, and whatever that value is, but it's a constant. So once it's a constant, it means that we are only maximizing 0 to T. This is just a constant. It's only for comparison purposes. If that's the case, we know that there is no wealth is going to be left, and whatever wealth is going to be left will be 0, and the value of that is this. That's for comparison purposes again. If there was a bequest function, there may be a value for leaving 0. For whatever, the guy may be very happy that he was so smart that he consumed all his wealth down to 0. But whatever. So what we did was because of this condition, we know that optimal solution would actually leave wealth 0. So we're gonna solve the problem with the constraint WT equal to 0. It could also be WT bigger than or equal to 0, in which case we'll also leave the wealth 0.
Excuse me, Professor.
Yes.
I think we have already.
This part was done. Yeah.
I know it's done, but I'm going back to it to connect it to the problem.
Okay. Oh, okay. Yeah. Okay. Thank you.
Remember, we are just going back to this problem. So then, when we connect to the next problem, you will see what's going on. That's basically the exposition value of this exercise. Okay.
Got it.
So what we did was remember, because this is a fixed endpoint problem, lambda T was beta to be obtained. And basically the way you obtain the beta is you find the consumption, which is in terms of beta. The consumption will be in terms of beta because consumption is 1 by lambda. 1 by lambda is in terms of beta. So now we can manage the we can find the value of beta, so that will adjust the consumption in such a way so the WT becomes 0. That's how we find the value of beta. So what we do is we put this consumption in a state equation. We solve for W. When we solve for W, we have a wealth W star T, which is also a function of beta, because for any beta, that solution gives you this. So now we can find T equal to T. So when we put T equal to T, capital T, when we put capital T, then W star T, we want it to be 0. When we make this to be 0, that gives us the equation in beta, which is this equation, and that gives us the value of beta. So what it says is that when it's a fixed endpoint problem, then we can manage the beta so that the value of the wealth at the end is exactly 0. That's how you solve the 2-point boundary value problem. Now let's see what happens. In this problem, we have a half fixed problem. It's not completely fixed, but it's not completely free. And when you have that problem, then we know that the boundary condition on lambda will be kind of half fixed, because this is not completely free. So we cannot fix lambda. And this is not completely not free. So we cannot leave lambda to be free. So because this is in between case, lambda t will also be an in between case. These are kind of intuitive reason of why the math works in some sense. Now, remember, I went to example 3.2. Example 3.2, we found the value of beta. That value of beta is exactly the value that will give you 0 wealth in the end. Clearly now, if b was 0, certainly we will have the same solution as the previous solution, right? If b is 0, then that in the previous problem, b0 will be b of 0, which is the bequest of 0, will be exactly 0. Because right now we define the bequest function not a nonlinear function, but a linear function. Okay, but even if you define a nonlinear function, it should still be okay. We can still solve the problem. But to just make things simple, if this is the way the bequest was, then b of 0 is exactly 0. So that's how I connect the problem to the previous one. Okay. So that problem with w equal to 0, wt equal to 0 will exactly give us the previous objective function, because b of 0 will be 0. Okay. So then what happens is, clearly at b equal to 0, the previous solution is still good. But if b is slightly bigger than 0, maybe the previous solution is still good, because I don't put so much value to the bequest. So the issue becomes, what is the threshold value of bequest? Which is exactly the point at which the individual will be indifferent between, well, not indifferent, but individual will leave the value at that b exactly equal to 0. So if b is smaller than that threshold, the wealth will be 0, and previous solution is still good. And if b is bigger than 0, no, bigger than that threshold, then wt will be bigger than 0, and that solution is no longer good. And this gives us a clue how to solve this problem. So clearly, if beta is bigger than or equal to b, this is the beta. So if b is sufficiently small, by sufficiently small, we mean b is less than or equal to beta. Well, if b is less than or equal to beta, notice this condition is satisfied, because this says lambda t is bigger than or equal to b. And if lambda t is equal to beta, which was the previous problem, then beta being bigger than or equal to b, this condition is satisfied. If this condition is satisfied, then that is satisfied for any wealth, certainly satisfied for wt star equal to 0, which is what it would be, because beta could be, b could be strictly smaller than beta, in which case beta will be strictly bigger than b. If beta is strictly bigger than b, then lambda t minus b will be strictly bigger than 0. And for this condition to be satisfied, w star t has to be equal to 0. So exactly at the boundary, when beta is exactly equal to b, then both conditions are satisfied in the sense that this is 0 and this is also 0. Okay. So that beta bigger than b, the problem is solved. We already know the solution of the problem from the previous example, which is example 3.2. So the only thing that remains to be done is what if b is sufficiently large? Sufficiently large means now it becomes bigger than, strictly bigger than beta. Well, if it's strictly bigger than beta, then notice what we do in example 3.2. We manage this beta. This beta was down below. So we fudge the beta so that the consumption is adjusted in such a way so that W star at capital T becomes 0. So beta basically gives you a regulation of consumption to manipulate the wealth at WT. Now, since B is bigger than beta, I could exactly set lambda capital T equal to B. Since B is bigger than beta, that's going to reduce the consumption from 3.48, because 3.4 it is for the beta value which is given here. But if B is bigger than that value, then the consumption will be in the next problem, which is the problem we are now working on. Consumption will be smaller than that. Smaller than that will exactly leave whatever wealth it will leave. Because we remember WT is free as long as it's bigger than or equal to 0. So we don't care how much mathematics doesn't care how much WT is left. All it cares is regulate the consumption. So now what we do is we exactly set the value lambda T equal to B now. When we set lambda T equal to B, remember this quantity will be 0. And when this quantity is 0, W star T can be whatever it wants. But whatever it wants is exactly what B will give you. Because if in the previous example, if you change the beta to B in that consumption formula, then the consumption is fixed. Fixed in the sense consumption is known, not fixed, not constant, but the consumption path is fixed. When the consumption path is fixed, then we can solve the problem for W dot, and whatever wealth it gives you is okay, because every wealth will satisfy this condition. So that's what we do. So now we put lambda T exactly equal to B. When we put lambda T exactly equal to B, C star T will be exactly this. Remember, beta has now become B here, if you compare with the previous problem. So the C star T exactly becomes this. And when you put this C star T, the lambda T is exactly this. And now the W star T can be solved is exactly this. And now you can compute, you can put capital T here and find whatever the wealth is. And that wealth has to be bigger than or equal to 0 anyway, we already know, because this B is bigger than beta. So the consumption in this problem is bigger than the consumption in the previous example. And the previous example left the value 0. So this example will leave the value bigger than 0. And whatever that bigger than 0 is this quantity. I hope you got some idea by this example of the value of this transversality condition. It is now have an intuitive explanation of why we have this condition. So this condition allows us both sides now, whatever the value of B is, if it is smaller than beta, then we know that this condition is satisfied with strict inequality, and so W star T will be 0. If on the other hand, B is strictly bigger than beta, if B is strictly bigger than beta, then we want to just set this equal to B, because remember, when B is strictly bigger than beta, we know that wealth at capital T will be strictly bigger than 0. We know that. If it's strictly going to be bigger than 0, then this quantity is strictly going to be bigger than equal to 0. If this quantity is strictly bigger than 0, then only way to satisfy this condition is by setting lambda t equal to b. And that's what we did. Any question here? Because this is one thing that I take pride of in this book is that I am trying to explain things which you will not find in control theory books in electrical engineering literature or math literature, because they will just prove a theorem and that's where they end, and then they just continue on to the next chapter, next problem. Here we are actually giving you, we're giving you teeth to bite into the problem and understand, why things are the way they are. So if there are any question right now, please let me know, and we'll just move on to the next problem now. Yeah, this basically says that we instead of using what we did, we can also use 3.42 of table 3.1. What we use is that big table at the end that we left last time, but we can go all the way to the box, which is called the maximum principle, which is the same. There is lambda t is b plus alpha, but then alpha. So this condition can be written in terms of alpha, because if this is b plus alpha, then this will be exactly alpha, and alpha times w star t equal to 0, and so that's what that is. So they are the same. So the previous time we solved the problem by going to the problem that was solved for free endpoint problem, not the fixed endpoint problem. Okay, but we're not going to solve two problems all the time, right? We want to just use the maximum principle to solve the problem given to us, right? So for example, here we could have solved problem x2 equal to 0 and then come back again. But if you put x2 equal to 0, it doesn't have the same interpretation like the consumption problem where we have meaning for every term. Here it's just the abstract problem where there's no physical meaning to it in some sense. And so without any physical meaning, we lose the intuition that comes with it. But in any case, here we solve the problem directly. So now we have a half fixed endpoint problem, if you call it. I cannot call that in a book because that is not the terminology that people would use, but certainly you know what I mean. So now we have a Hamiltonian. Now there's a bang solution in this case, which is predicated on this lambda, and lambda dot equal to 1, so we can solve the problem for lambda dot equal to 1 easily. But we have a condition on lambda. Because this is half fixed, we have a complementary slackness condition. And the complementary slackness condition, we just found some nice meaning in the previous example. So we have some confidence that this is good. Of course, it's been proved in the literature. We don't prove these things here in this book, but it can be. So now how we solve this problem? We know that lambda is going to be monotonically increasing because of this lambda dot. If it's monotonically increasing, then by bang solution, it means that the control can go only from -1 to +1 if it switches. That means three possibilities now. Control can be -1 all the way. Control can be +1 all the way. Or control can be -1 and a +1 and a switch somewhere in between. It cannot be 1 and a -1. It cannot start with 1 and switch and become -1. So we have ruled out one possibility. We now are left with three different possibilities. We ruled out one possibility. But the amazing aspect of it is that once you rule out that possibility, the problem becomes manageable. Okay, so we rather don't solve all of those because all of those three can be almost taken into one way of looking at this problem. So let's do it, what I mean by this. So because it's monotonically increasing, there may be some switching point T star. And that T star certainly has to be less than equal to 2. So T star has to be less than equal to 2. And if T star is whatever it is, then I can solve this problem by putting -1 until T star and then +1 after T star. When I solve this differential equation, I can easily see that this is my U star. And the solution for that is going to be this. Because if you put u equal to -1, we begin with 1. So xt will be 1 minus t until T star. Then we start at T star with xt star equal to 1 minus T star. And then we have a new problem that begins at T star. And xt star is 1 minus T star. And u equal to 1. And we can solve the problem. So by doing that, we find the trajectory xt for the entire time t. And by doing that, we can also find lambda t, which is because it's 1. And at T star, it has to be, so it could be T minus T star. But we don't know T star. T star is just a constant of integration. When you solve this problem, lambda dot equal to 1, T star becomes, it's a differential equation with no boundary condition, so T star becomes a constant of integration. The constant of integration would require a boundary condition to solve. But the boundary condition of lambda is not exactly a boundary condition in the theory of differential equations. It is kind of a boundary condition that depends on this. So it's like a 2-point boundary condition. So we cannot solve this without solving this. That's what it means by 2-point boundary value condition. Means the two equations are somehow linked and we cannot solve one without the other. And the boundary condition is in some way mixed. So theory of differential equation usually don't get into that, but they could. The beauty of this T star less than 2 is that it allows me all 3 possibilities except the one that we ruled out. All 3 possibilities is the following. If I set T star equal to exactly 2, then the control is -1 all the way because there is no time after that. So T star equal to 2 allows me -1 control all the way. On the other hand, T star equal to 0 is also allowed. T star equal to 0 means the control is +1 all the way because this is 0. So this has no interval. So we have I mean, at one point you can call it -1. It doesn't really matter. But you can also, so you can set -1 at one point and then you begin with +1. So that means +1 all the way, right? So that T star, the way we define, has all 3 possibilities. Remember, we ruled out the +1, -1. We ruled out the switch from +1 to -1 because that would not be fitting into this in any case. So we have all the problems by this. So all that's left is find the value of T star. And we know the value of T star is easily found because at the time we switch, which is T star, that says at the time we switch, lambda has to be equal to 0. Because that's the only way we can have both -1 +1. So on that side it'll be -1, on that side it'll be +1. So the lambda at T star has to be equal to 0. Well, if the lambda at T star has to be equal to 0, that will gives us the way to solve the problem. Okay. So let's continue. So now we have xt. And xt has to be equal to so there is a fork now. So once we have this situation, we have 2 cases. One case is the T star is strictly less than 2, and the other case is the T star is exactly equal to 2. So we can take any case we want because only one of them will be optimal. If we take our own case, we'll find it doesn't satisfy the condition. And if you take the right case, we know that it satisfies the condition. So in the book, for one reason or another, I have always chosen the place. I've chosen the case that happens to be optimal. But it might be a good idea for you to look that and see whether that's optimal, whether we can find a contradiction. I choose not to do it um, um, just for a variety of reasons. One is a space. don't want to, you know. But maybe it's a good idea to do it on one problem one time. Okay, case one, lambda 2 is 2 minus t star, which is bigger than 0. We know that. And because t star 2 is bigger than t star, so 2 minus t star will still be bigger than 0. And so that means x2 has to be equal to 0. Because if lambda 2 is bigger than 0, then by complementary slackness condition, x2 has to be 0. Because lambda 2 is strictly bigger than 0. This is strictly bigger than 0. So x2 has to be equal to 0. So we have x2 equal to 0, but we already know what xt is. So we put t equal to 2 here and set it equal to 0, and we get this. That gives you t star equal to 3 divided by 2. And once we have 3 by 2, it satisfies what we assume to be t star less than 2. And we do not have to deal with the case 2. Both cannot be optimal. Now, if t star is less than 2, it's exactly 3 by 2. When it's 3 by 2, we also solve this problem because we just set this equal to 3 by 2. So exactly at 3 by 2, this lambda t will become 0. And now we have a picture. So lambda t is t minus 3 by 2. J star can be easily computed. And we have a picture now. The picture was 1 all the way up to 1.5. And then it goes to like this, -1, then +1, and it exactly goes to 0. And lambda goes all the way from here to there. And at this particular point, lambda t crosses the abscissa or the 0, lambda t becomes 0 at this point, and then it continues on to this point. So we have both terminal values here. One is 0, one is half. Everything is satisfied, and we are done. What I want to do next is I want to find the marginal value of lambda, because lambda is the marginal value interpretation, which means that if I change the problem a little bit, I should be able to tell you how our problem will be affected. Okay, so since we require this to be bigger than 0, remember value function vxt only can be computed for those value of x at time t so that there's a feasible solution. What we do usually is we set any x at a t pair for which there is no feasible solution, we set that equal to -infinity because we are maximizing. So if there's no feasible solution, then that's the worst it can get, and we just set it formally equal to -infinity. It only means there's no feasible solution. So it is easy to find the value of x and t pair. So this is xt pair, so that we have a feasible solution. Because just looking at the picture, we can easily figure this out. If x is very high, no problem, because it will. Remember, we need to have x2 bigger than or equal to 0. So you can easily see that if I started with the x, which is so low, that even with +1, I can only go this far. I cannot even go to 0. So you can easily see that if I go all the way from 0 with the +1 control all the way down, we will come to an x value that below that x value, I have no feasible solution. Above x value, I have a feasible solution. So I can restrict my x value at 0 to be below that. But remember, I have to solve the problem for every t, not just for 0. So basically, this boundary, that boundary goes all the way to here. That boundary, anything below that boundary will not have a solution, feasible solution. Let me see what I did. Oh, I wanted to show you a couple of things. I already went through the existence issue, right? I gave through the paradox with for you, right? I went through this, right? Did we go through this exercise? I mean, anyone?
Yes, Professor, we did.
Yes. Now what we didn't do is this. So what I'm going to do is I did some chart for myself, so I will show it to you later. So what we're doing now, we already know that any value of xt in this region is no good, so we can easily regulate ourselves, which is what. So we can take value xtx, and then we use the notation that we created in example 2.5. The notation was that I start with the xt value for any time t. So let xt be x at some time t. Then the control u star xt for any s which is bigger than t is going to be -1 and a +1. Now, there are two ways to do it, at least for this problem. One problem is that you can start with x and a t. So you can start a problem at some x and some t. So this is, let's say, t. And you declare a new time which makes this t equal to 0, call it a tau. So that makes this t equal to 0. And then you resolve the optimal control problem just like we did here. Because our book does not, some books actually begin the optimal control problem for any t, small t. We don't do that. Our problem, right from chapter 1, we begin the problem at t equal to 0. Our initial time is given to us. So if the initial time is some t, we can always make it to 0 by a transformation of time and convert the problem into a problem with 0 time, beginning 0 time, and resolve the problem using maximum principle. So that's easy to do. But another way is more because I'm trying to not only give you, I also want to give you a lot of intuition in what's going on. Okay. So what I'm trying to do is, we know kind of how to solve this problem. The problem sort of says that if x is high enough, I want to start with 1, -1, and then go to +1 to make it 0. Okay. If I'm going to start from very high, then I just go -1, and wherever I end up is fine, because it's going to be bigger than 0 anyway, and there's nothing I can do. So that is easy to do. So at one point, if x is exactly there, then I will just choose -1 and just go here. So all of these problems where x is sufficiently high are easy, because the control is just -1 and we are done. And we can find the value function for that, okay? Anything below x, I will go here and then go there. So if my big upper, let's say I'm 1 plus epsilon, then I will go somewhat like this, and I will go a little bit here, and then go here. So what I'm trying to say is, if it's epsilon, somewhere I have to switch so that it backs to 0 again. Okay. So that would be our new optimal control, and you can sort of see why it is so. Okay. So what I'm going to try to do, because remember, we want to find the value of marginal value at any time t. So we're going to, so what we try to do, one way to find out, in order to get the marginal value, I can change this initial value x from 1 to 1 plus epsilon. And if I change from 1 to 1 plus epsilon, Then lambda 0, I already know what lambda 0 is. Lambda 0 is exactly minus third, minus 1.5. And so my objective function should change by minus 1.5 times epsilon. That's kind of my argument, because lambda 0 is exactly that, so it will multiply by epsilon. There may be second order term in epsilon, but they will all go to 0 when epsilon goes to 0. Remember, all marginal valuation, when I put value of marginal value at 1 plus epsilon, it is defined, theoretically, it's only defined as epsilon goes to 0. Sometimes maybe epsilon is sufficiently small, so the epsilon square terms don't arise. But if they do, it means that exact marginal value can only be for any small value of epsilon, which means epsilon going to 0. Okay, that's how you define the derivatives. So derivatives are limits of epsilon going to 0. Okay. So I need to find out from any xt an optimal control, an optimal state, because only by doing that I can compute the value function. So the way I do it is kind of like this. So let me show you what I did. You can resolve the problem by transforming the time, and you will get this solution. But I think it's a nicer way to look at to see. Can everybody see this? This whole picture is there in front of you?
No,
Yes.
it's not all. We cannot see the graph. We could only see the equation.
Yeah.
Now?
It's fine now. I think yes.
Okay, so let's begin with this. So I'm going to go like this. This is my t, and this is my x. This is the point where I'm going to begin my problem, okay? If I begin my problem at this point, you know my control, given our insight that we have, my control should go like this, and somewhere at s star, because remember this is t, s is any time after t, so at some star, it will switch and become 0 at 2. You see, I'm begin with any x and any t. My control, my state trajectory should look like this. My control should be -1 and a +1, and I should find an S star. Well, S star is easy to find because this time and this time has to be equal. Because if you go from 0 to -1, you should go only so far so that with +1 you go back to here. Okay, so we already know what a trajectory is. That's going to be optimal. All we have to do is this S star. But S star is exactly equal to, so remember, if you begin with from x to t, then at t plus x, remember it's going -1. So at t plus x, x is going to become 0. So this is your t plus x. Okay? And the difference between t plus x and s is actually s minus t minus x. And you divide by 2 will give you this amount. So you can find S star equal to t plus x, which is this. Remember, this is S star. Okay, so S star is t plus x plus that divided by 2, which will give me this value right there. Is that clear? Any question here? No question. So that's what I did here.
Professor, do you mind take a picture or for this graph and send it to us later?
Sure.
Okay, thank you.
Yeah, can do that. I'll take a camera photo and send it to Gautam. Okay. Is that okay? So I have u star t x t s is -1. So basically, I'm basically saying it's -1 up to here, and then +1 from here to there. So it says u star of xt, which is the initial condition, s, which is the time, it's -1 from s going from t, which is this t, all the way to this point, which is going to be half x plus t plus 1, which I compute right here. So we know -1 goes from t to this point, which is S star. And after that, it goes to 1. So from S star to 2, from S star to 2, the control is +1. And trajectory is very clear. It is like this and like this. So you can find the trajectory to be very clear. So that part is easy to do. But you know, this basically derives, if I begin the problem here, I can put a new time tau and the problem becomes exactly like this. And I can apply the maximum principle. I can do these two cases. I will get the solution. Okay. Then change the tau back to the new time. And when you change the time to the original time, this will give you the solution. This is the solution. So you can do that way. It'll be a good idea if you're somewhat interested in doing both ways, and you think that will give you a more understanding of what's going on. Please go ahead and do it. But once I have x star, you know, my objective function is exactly minus x dt. I know exactly x, so I can find the value function. So the value function, these examples, once again, are found nowhere. You will not find these into books because I'm trying to compute the value function, because the maximum principle people don't care about dynamic programming. In fact, some books of maximum principle don't even use dynamic programming. They derive the maximum principle directly using math and then just continue on. I'm connecting these two guys. I'm not giving you all the proofs because the proofs by dynamic programming are limited to some extent. So I'm only giving you the feasible region for x bigger than t minus 2. You can do other things, but just to show that that's enough for me. Vxt is from t to 2. This is minus of that trajectory, SDS. And then from t to this point, okay? So the t to 2 has two parts. One is t to this point, which is S star, and the other one is from S star to 2. And I have a trajectory. So I use this trajectory for the first part, this trajectory for the second part. As you can see, this is the second part, this is the first part. These are easy to integrate. So I integrate. And for x less than t minus 2, there is no feasible solution because Vxt is minus infinity. So now we can verify that for 0t less than 3/2, the value function is given by this quantity. And I can take the derivative of that with respect to x. And the derivative gives me exactly t minus 3/2, which is exactly lambda t. So now you can see what lambda t is. So here we didn't have to go epsilon root at all because this thing is good for any kind of value of epsilon as long as epsilon doesn't go all the way up to a point where there is no switch point. And even that may be okay because the switch point, this thing will become 0. If there is no switch point, everything will be here, and so it will still be okay. But anyway, this is our lambda t. And so we have now a complete example in which we actually find the value function to be this. And I think this is going to help us to understand a little bit more of what's going on in chapter 4. Okay. The free terminal time condition is this condition. And there are ways to prove it. But I'm going to give you, now that we have some understanding of what's going on, I'm going to give you some reasoning behind that condition, because this condition looks kind of ugly. It doesn't say anything in terms of, how. But you know that one way to look at it is the following. I can solve the problem for any given t, capital T. When I solve the optimal control in principle for any given capital T, then J of T will be a function of that T. I can call it a J star of T. Okay? So now nothing is, X is gone, lambda is gone, everything is gone. I solve the problem. I compute the objective function. The objective function only has one thing, function of T, because everything else is in terms of that T. The optimal control is in terms of the capital T, the state is in terms of capital T, the function fx ut, x star T, u star T will all be in terms of T. So when you take the integration, it will be J star of T. And I can then take the derivative of this J star T, first order condition, and set it equal to 0. When I do that, I should get this. So that's one way to look at it. But remember, for any general problem, you're not going to find an explicit solution of x star T. So all of this is going to be implicit functions of capital T. Then you take the integral, it's going to be an implicit function of capital T. And then you have to take the derivative of this T, and it may be somewhat complicated. Not only that, sometimes you may not be able to find that implicit function because you need to find the optimal control, and it may not be, all you can find is a necessary condition of optimal control using maximum principle. So you may not be able to get all the way to the optimal control. But that is in principle how to understand this. And I'm going to give you this following way to look at what's going on. So what I'm going to do is I'm going to assume that we found a T star, and I'm going to change the T star to T stars plus delta. That means I'm now going to have a new problem where T, the horizon of the problem is not T star, but T star plus delta. And then I want to find the value of the new J with this new horizon. And I want to show that if I increase to delta, then the objective function will go down, because that's the only way T star will be optimal. I could also do the other way, T star minus delta. Again, I need to show that the objective function will go down. But in order for me to show the J star of T star minus delta and the J star of T star plus delta, I need to solve two control problems again, because I have a new time. So that's kind of hard again. So there is an interesting way to look at this problem is this. Because delta is going to go to 0 anyway. This is a first order condition. So I can fudge a little bit. And the fudging a little bit is not going to change my J star T that much. And so I may be able to do this without solving these two problems. And even if I solve these two problems, I don't know if I can take the derivative. It's not clear to me that that's so easy. So let's do the following. If I do the T star minus delta, I can assume the same control. So first of all, let's assume that we have solved the problem and we found the optimal T star. Okay, so that's our beginning. Okay, we already know that. So now if I put T star minus delta, another T, then I can use the same control. because my control is defined up to T star. It's not defined beyond T star, but it's defined up to T star, so I can use the same control up to T star minus delta. It's not optimal. Remember, if I resolve the problem for T star minus delta, I may get a different control. But what I'm trying to do is to use the same control that I found for T star and just chop it off at T star minus delta. So I ignore the portion of the control that is beyond T star minus delta. But T star plus delta, I need to find some control from T star to T star plus delta. So what I'm going to do, I'm going to say, let U star T be exactly what it was at T star and keep it constant from T star to T star plus delta. Because I need, in order for me to compute J, I need a control all the way to T star plus delta or T star minus delta, depending on which T I take in this interval. But if I do this, then I have defined at least a control, feasible control, for all of these problems for any T here. It may not be optimal, but it is a feasible control, and it's not so far from optimal. It is hopefully close to optimal that we will be able to still get there. Okay. If I did that, then that is easy to do. Remember now, I don't call it a J star T, but now I take any T between these two guys, and I have this fudged control, which I call U star T and X star T. And I of course, I can find this. I can compute this integral in principle, and I call it J of T for any T. It cannot be J star because these are not optimal for that T. They are optimal for this T star, and they are kind of, again, I fudged it here. Okay, so I did that. But U star T is continuous at T star. And so X star T is continuous. It's continuous clearly because I set it exactly to U star T star. So it's continuous. Because it's continuous, then X star is continuously differentiable because X star is the solution via differential equation. So it integrates a continuous function. When you integrate a continuous function, you get a continuously differential function. So X star is continuously differentiable. So is J of T. So I can take the derivative of J. J prime T star, which is to be defined as G of J dJt dt equal to 0. Remember now, I'm taking the derivative of this guy. And because T star is optimal, it must satisfy this. Okay. Now, otherwise, because if this was not 0, then we would have this bigger than 0 or smaller than 0. The former situation would allow us to find a T for which Jt is bigger than Jt star. Remember now, if this wasn't 0, then it will be like this. And if it is this, then we're saying that it is this, even though we did not use an optimal control for that T. So if this is D, then J of T is bigger than Jt star, and it would certainly, and so T star could not be optimal, since choice of an optimal control defined on interval 0 T would only improve the value of the objective function. So we are okay. Likewise, the latter situation will allow us to find a T star in this for which Jt is less than Jt star. So by taking the derivative of 3.78, we can write 3.79 as this. Because you can take the derivative inside the integral, and when you take the derivative inside the integral, we get this, right? We get inside the integral, it is just f sub t. You know, because this is t, so it's just f. And this will have two terms. First, you take the derivative with respect to x star t, so that will be s sub x. And then you take the derivative of x star t with t, and that will be x star dot t, which will be lambda. So this will be lambda times s sub x, x star dot. And but s sub x is exactly lambda, and x dot is exactly small f. So this is lambda times small f. But the lambda times small f, and this f is exactly Hamiltonian. So this is the Hamiltonian, and this is already s sub t. So we get exactly Hamiltonian plus s sub t. What I'm trying to say is that even with a control which may not be optimal, I'm able to find a JT which is bigger than JT star. So clearly, if I found an optimal control, I could do even better than JT star. So even with a little bit non-optimal control, I was able to do better than if I were to resolve the problem for T star plus delta. I can only do better. So I can improve this guy. What I'm trying to say is I found this JT by some fudging. But if I did not fudge, this JT will if I had exact optimal control for that T, I would improve on this JT. It'll be even bigger. So that means that something I can do is even bigger than that. And if J star of that T, this is JT, J star T is even going to be bigger than this. And so J star T is bigger than J of T star. Well, then that means that that T star cannot be optimal. Okay. I think it will be a good idea to put maybe this to be J star of T star. And then I have one more step here to say J star of T star plus delta is bigger than equal to J of T is strictly bigger than J star T star. So that line is, I'm putting that line here in words, but it might be better to do that with one more term in here. So maybe I will make a few small changes. Yeah, this is not going to be a fourth edition, but some changes are allowed because these days the books get printed. They don't print like 1,000,000 copies of the book anyway. They print maybe 100 copies, sell them, and then pick another 100 copies and continue on like that. So every time they have a reprinting, they can change some stuff a little bit. So I'm thinking maybe I will make that. Okay. Well, this one, the other way that I told you, is done in this paper of mine. And that is not easy. That paper required some work, and I don't know why we just put it in some journal that is not recognized as much. It probably deserved a better place to be there. But on the other hand, people have proved, they could only say, okay, this is one proof, because these conditions have been proved in the literature by other means. And so it's not like it's just giving another proof. So again, some journal may say, okay, this is just another proof. But I think it probably deserved a better place. Okay. And then this is straightforward. If t has to be bounded between t1, t2, then intuitive way of doing it is like this. So again, to prove again, this would require Kuhn-Tucker conditions, and that would even be more complicated than what I did here. So all of that may require quite a bit of a mathematical machinery to even get there, but you know roughly that that's what's going to be. If it's interior solution, then the first order condition, the first order condition. If it's a boundary solution, then first order condition will have inequalities at those boundaries. Okay. Any question? Because this is the only way we can show you now that this ugly looking condition, I wouldn't say ugly, but it doesn't look like it's a first order condition, you know. First order condition looks like this. And that one doesn't immediately translate to this. Oh yeah. Now we solve the problem and find a t. So now we have max of u and a t, max over control and t. We have this problem, and we have terminal value. We have x dot, we have initial condition, and now we want to find out the optimal t. So Hamiltonian, x minus 2 plus lambda times this. Lambda dot is -1. Lambda t equal to 1 because, because it's a free endpoint problem. So free endpoint problem, lambda t equal to 1, which I can solve lambda t exactly. I can solve. But remember, I'm solving in terms of t. So I'm solving the problem in terms of t right now. The optimal control is given by u star t, bang, this. So now what I found, interestingly, that u star is 1 up to t minus 1 and is 0 after t. So for any t, this problem tells me that I should go all the way to t minus 1 with control 1, and then I switch to 0. That's the idea right now. So let's do that. If I do that, the optimal time t star must be determined. And so I apply this condition because see what I can do is the following. There are a number of ways to skin this cat. Okay. If I knew this control, then I can literally find the j star t star. I mean j star t. I'm sorry, j star t for any t. I can integrate this x dot here, this one. I can integrate that and find j star t, and then take the derivative of j star t and find t star. Okay, that's one way to do it. And you might want to try to do that, because in this case you can actually integrate it. You can find the t and you can take the derivative and you solve for t star. You can do that. It would be a good idea for you to do it. But what I'm doing is using the transversality condition, because the other one is to say I find the solution for any given t and then solve the problem, and then the problem is just a one variable optimization problem, which is a calculus problem, and I take the first order condition to find t star. But I'm using now the optimal control condition. So I use the 3.77, but u star t star is exactly 0 from here, because remember u star t star is 0. Remember this is 0 all the way to t. So at t star is going to be 0, and I need that u star t star in my definition of 3.77. So the 3.77 is applied this way. I basically apply the Hamiltonian x star minus u star lambda . So you can put x star minus u star lambda this, but u star t star is 0. U star t star is 0. So I get x star t star minus 2 equal to 0. So it says that the first order condition of this Hamiltonian, which is this one, it is basically equivalent to x star t star equal to 2. That means as long as I can find x star t star equal to 2, then that t star is optimal. So that's easy to do. I find for x star t, and then I put capital T here. The capital T then gives me x star t star minus 2 to be 17 minus 1.5 t star minus 2, which is coming from here, and then 2 equal to 0. So I use this for x star t star. I put t star. I use this formula, and I put t equal to t star, capital T equal to t star, and this equal to 0. And that gives me t star equal to 10. So the optimal solution is use control 1 up to 9, up to t time 9, and then from 9 to 1 use the control 0, and that's optimal. So I found t star to be 10. I found it optimal. So this is an example that I give you. This example is so simple that you can actually do the other way, which will be different in this proof. It will not be a proof, but in an example, it'll give you some idea of what is going on. I think this would be a good idea to put exercise. So new exercise. New exercise relating to example 3.5. Where are we time-wise? We are 1 hour and 9 minutes, so continue. This problem, example 3.6, is not a problem in management science and economics. But this is a problem that is found in every optimal control theory book. And it is a problem that is interesting because it has a rather interesting solution, not so easy to solve, but mathematically it is easy because it can be explicitly solved, completely explicitly solved. Nothing remains to be solved in the sense that everything is completely known about this problem. And it is also a problem that gives you an idea of more complicated problems that have been used in surprising ways that I will tell you later. So what we are looking is the following. We didn't do this, right? We are discussing this problem now for the first time. We have a train.
I think we did.
Yeah, Professor, we discussed it last day.
Oh, so we did that one. So
Yeah.
So we skipped some of the other things and we did this one, right?
Yes.
Okay. So then we will move to what is left over. Let's continue. So are there any questions? Because we might have rushed into it. I didn't see that in the lecture video. Maybe it's in the beginning somewhere. Okay. Gautam, please check that, huh? Okay. So as I mentioned, that this is the problem that also is a beginning of what was done in terms of getting a rocket all the way from Earth to the moon. Moon being the zero axis of the train, but it has coordinates, and you can have three-dimensional coordinates in the space, and you can have a Kennedy Center coordinate. So you have a problem with XYZ coordinate. That's where the thing begins. And you have another coordinate XYZ, the other place. And so what do you need? You need three equations, X dot, Y dot, u dot, x dot, y dot, z dot. Those are the velocity at any point x, y, z in the space. And you need the acceleration, which means you need a thrust, how much fuel to burn, at each point in time to regulate these velocities. So you will have 6 equations, okay? The minimum 6 equations are needed. So if you have these 6 equations, you can actually find the force used at every time t between when the rocket leaves the Earth all the way to the moon. And the equations, of course, would have gravitational force into it because this train doesn't have a gravitational force. But you can easily find those equations using physics, which is not very difficult to do. From any point to any point, you have easy to figure out because there's a weight of the moon and there's a weight of the Earth, and then there's a weight of the aircraft. And you can use the Newton's law of finding the gravitational force pulled by the Earth and the moon onto this rocket at any point in time. And so you can write the dynamics of this rocket using simple physics, actually, not much complicated. And then you have a complicated equation in terms of nonlinear system, which may not be explicitly solvable, but you had computers that would solve those problems and give you the numerical value of the optimal control at each point in time in the space. Okay, and then you have a, and then you can, instead of minimum time, you can do a minimum fuel problem. The control doesn't have to be minimum time. Maybe it is some function of minimum time and the fuel required. The fuel may be not so important given the amount of money that was spent for setting up the SOD, and lots of people got involved, and you pay all of them. So fuel is probably the least important part of it. But there may be other issues of stresses and required that may be used to see the stability of the system and stuff. So it is more complicated than it sounds, than I make it sound. But it is there. The idea is there. The concept is there. And in fact, it was used. It's not that it's not hypothetical anymore. This is exactly what it was used. They use optimal control theory to get there. So infinite horizon. So t equal to infinity. First of all, we need to have rho bigger than 0. Otherwise, problems are hard to solve. And the reason are because, no, I mean that if you change t from t to t finite t to infinity, then non-stationary infinite horizon problems are hard to solve. By non-stationary, I mean things depend on time, explicitly depend on time. And in our problem, it means a forecast of demand all the way to infinity in, let's say, inventory problems. But who has a forecast of demand all the way to infinity? It is almost impossible. And so usually you have a stationary problems, which means you can say, okay, forecast grows at 5%, or is it sinusoidal, or whatever. But that some way of simplifying that is required in order to solve those problems. Mathematics is there. I mean, Stephen Shreve, my co-author, has a book that goes into this kind of problem, which are require quite a bit of a mathematical notation even to get there. So we consider stationary finite horizon problem. The stationary assumption means that the state equation, the current value adjoint function, and the current value Hamiltonian are explicitly independent of time. It's also reasonable to assume that there is no salvage value. Although there are times when you might need it, and we will see those times in finance, which is chapter 5. I also want to show you that the stationary concept is different than autonomous system that was introduced to you in exercise 2.9. And because we are using discounting, So discounting always have a time dependence, but our stationary system, remember I'm saying current value adjoint function is independent of time, but the standard adjoint value is not function of time. Yeah, it will be a function of time, and so the system will not be autonomous, but it will be stationary in our setting. So we're not autonomous system is not a concept that we are used very much in our literature, and so it's basically relegated to an exercise 2.9 just to tell you that there is such a thing called autonomous system, but I wouldn't worry about too much. So here's a stationary infinite horizon problem. Remember, I don't have a t anymore here, but there's a t here, so it's not autonomous, but you will see it's stationary when we find the maximum principle. You will see the maximum principle of phi xu. The Hamiltonian will be independent of time because this is independent of time, and lambda t again will be explicitly independent of time because it will be minus delta h of delta x. So and the constraint also doesn't have a t in there, so this is our stationary problem. We also don't have a s, which is the salvage value. So if we go all the way to 2.73 and we put Sx equal to 0, we will see that we can get these conditions. We can get a limit t to infinity. This is the present value. This is the present value adjoint variable, which is equal to e to the minus rho t lambda t variable. And then this is bigger than or equal to 0. So this is one condition we can get. The other condition is it's almost like a complementary slackness condition at the end. In the free endpoint case, we have a free endpoint, so this condition is satisfied by having lambda t equal to 0 more or less. But in infinite horizon case, that becomes lambda pvt limit goes to 0, and that becomes this goes to 0. But notice this goes to 0 does not require lambda t to be 0. Because e to the minus rho t will also make it 0. So it only says lambda t should not grow faster than discount rate. So, so these are some of the conditions. If it's a non-negativity condition with xt bigger than or equal to 0, then we will have a transversality condition here. So all I'm saying is that if I'm given this problem, then some of the conditions that we have here can be easily translated into infinite horizon problems, and we can again use the maximum principle. I do want to say one thing, which I do not know I said it here or not, but it is said in the book for sure. And there's even an example somewhere. These conditions, if you look at these conditions are coming out of sufficiency conditions. And I don't have the time to switch back to the book and stuff, but you can look at it. These are the maximum principle is no longer a necessary condition for infinite horizon problems because the transversality condition is no longer necessary, but it is sufficient. So that's an interesting remark in the sense that we can find examples of infinite horizon problem which are optimal and do not satisfy the necessary condition. And that one of the exercises given in one problem is given in one of the chapters, maybe chapter 3, where you are very easily problem where optimal solution is very easy to intuit, and you show that the maximum principle is not satisfied in the particularly transversality conditions. Okay. So let's use these ideas for economic problems. Again, I have this problem. It's infinite horizon problem, and I don't want to go bankrupt all the way to infinity. That's a requirement. And this is a state equation. I start with the positive wealth. So the limiting version of maximum principle is sufficient for optimality in this case. Again, not necessary, but sufficient, but that's enough for us. So we have these conditions from the previous slide. And with t going to infinity in the previous solutions, we can actually find the solution of the problem like this. So we can sort of see that W star t is more W0, more consumption, but you can see that if R is bigger than 0, if the earning is bigger than the discount rate, then I earn more than discount rate, so my consumption over time will increase, because the consumption over time depends on, it's a constant fraction of my current wealth, and the current wealth is increasing because R minus rho is bigger than 0 when R is bigger than rho. On the other hand, if R is equal to rho, then my W star t is exactly W0 forever. And my consumption is rho times W0 forever. And notice, if my consumption is rho times W0 forever, I never consume the initial wealth. I only consume interest. So I keep consuming the interest that I earn from the bank, and I never consume any part of the initial wealth that I have. This is an interesting way to, I'll talk more about this later, but it's an interesting paradox. Because for a finite horizon problem, if I give you this condition, then I will consume a little bit more than interest in such a way that I will consume a little bit of a W0 every time, until the W0 becomes 0, until the wealth at time t becomes 0. That means I will consume the interest and a little bit more than interest so that I drive the wealth all the way to 0 at capital T. Why I cannot do that? Why I cannot, when R equal to rho, why I cannot consume a little bit of initial wealth all the way so that at infinity I have no wealth left? It's not possible. The optimal control will say that it is not possible. There is no way to consume the initial wealth. Because if you start consuming initial wealth, you will find that your consumption will become less and less, and it's less and less over a whole horizon of infinity, and you never make up in the consumption utility, which is discounted, because you're consuming a little bit more than the interest rate. But at some point, the if you consume your wealth, then the value you get cannot be compensated. That means that you cannot optimize the solution. So anyway, we'll talk a little bit more about it later. And so we can sort of see the value of the J star is given by this. And if R is less than rho, clearly your wealth is decreasing over time, and you're consuming again the same way. Excuse me. But if R is less than rho, your wealth is going to 0. Okay. When R is bigger than rho, your wealth is increasing, and you are leaving even bigger than initial wealth at the end, but you are not able to consume it to make it 0, because you're still consuming a fixed constant portion of your W star T. Okay. There's a concept of optimal long-run stationary equilibrium. It's a concept that says that in a stationary system, there are in a stationary system, there is some sort of equilibrium. By equilibrium, we mean x dot equal to 0, lambda dot equal to 0, where all motion will cease. Now, it is possible that in an infinite horizon problem, the equilibrium is an asymptote. That means for any initial condition, you may never attain the equilibrium, but you are asymptotically approaching it. That's one way to do it. Another way is that you you achieve the equilibrium at a finite time. So up to that time is called transient solution. And after this time, you stay constant. Consumption is constant. X stays the same. Lambda stays the same. And so you have achieved the equilibrium in a finite time, and then you stay at the equilibrium. So there are two ways you can conceive this equilibrium in any given problem. Either you achieve asymptotically, or you achieve it and then stay there, okay? But the solution of the stationary solution, the equilibrium, is a lot simpler than solving using maximum principle. No, not. I mean, it's a lot simpler than the transient solution. So if it is, in many times in economics, they don't even bother to solve the problem for transient. They will basically say this is the equilibrium, and then they go by equilibrium solution. So if you just want an equilibrium, you can just do this way. X dot is 0. So let X bar, U bar, lambda bar, mu bar be an equilibrium. Then you must satisfy X dot equal to 0, which is this. Lambda dot equal to 0, which is this. Mu bar satisfies the complementary selection condition. And for any condition, this is maximum for any U that satisfies this. I think I covered this a little bit too, but so we have a solution, if you can get there. But in economics, no economics book that I know have this condition. This condition. They just have these three. Arrow and Kurt's book that I grew up with, one of the economics book on optimal control theory that was around a long time ago. And that book only has this condition without that condition, and then they define the optimal long and standard equilibrium as a triple, because you don't need a mu bar, and the triple is basically given by this equal to 0, this equal to 0, and because there is no constraint on G, the Hamiltonian condition can be first order condition on Hamiltonian. So these three are very easy. And in example 3.40, the optimal solution of objective function can be easily obtained this way, because we can use those. I'm not going to go back to the problem right now, but these are easy to do that, and that's a triple. This is what is in Arrow Kurt's book. Example 3.7, which we had the example of the wealth and consumption. You can this is the one we just solved. You can see that for rho bigger than R, that means you earn less. You will see that you will consume in equilibrium. You will have nothing, no consumption, because that's equilibrium. So you may never reach that equilibrium. You just keep consuming, because you will keep consuming less and less. In this one, when R is less than rho, you keep consuming less and less. The C star T, this will go towards 0. So rho times W will go towards 0. So equilibrium will be a 0 consumption, but you will never reach it. You will always be in asymptotic case. That means you're approaching to smaller and smaller and smaller consumption, but you will never get to 0. If rho is less than R, you're going to go to bigger and bigger and bigger and bigger consumption, because this is increasing all the way to infinity. So again, you will never go to the equilibrium, because equilibrium will be infinite consumption, and you will only approach this infinite consumption. Okay. And if rho equal to r, then we already told you your equilibrium will be W0 rho times W0 and 1 by rho W0. And so you are already in equilibrium right from the beginning. So rho equal to r, you have an equilibrium right from the beginning. You have a constant wealth all the way to infinity. You consume rho times W0 all the way to infinity. And your lambda is 1 divided by rho down all the way to infinity. You can sort of see that you only consume interest. No, you only consume interest because r equal to rho, and you never consume the initial wealth. So there is a paradox like this. So look at a cake eating problem. So you have a cake of finite size, which is W0. So you have a certain amount of cake. And optimal solution is, in some sense, there are a number of people and you have to divide a cake in terms of maximize the utility or whatever. You just think about it. And it turns out that if all individuals are identical, then if you have a cake and if there are 3 individual or 4 individual, you will divide the cake into 4 equal parts and give 1 part to each. That's your solution, optimal solution. Now let the number of people go to infinity. When the number of people go to infinity, everybody gets 0 cake, right? Nobody gets a cake at all. The cake is still sitting there. And there's no optimal solution to consume this cake. The cake will just sit there and infinitely people will sit there empty stomach with nobody eating the cake. So there is a paradox of this kind that happens when you go from finite horizon to infinite horizon. And this paradox is somewhat similar in the sense that you are never able to consume, even though there are not infinitely many people, the time is infinite. So you're dividing the cake in time intervals. And because you're dividing the cake in time intervals, you cannot consume the cake at all. So W0 cannot be consumed. You can only consume the interest. Here's a different problem. Now I'm investing the wealth and the production function is log W. Instead of putting the money in the bank and earn interest, I buy a machine with my wealth, and that machine produces output. And log W is a well-known production function in economics. So I just put the production function in there, and my W dot is like this. And then I can use the stationary solution. The stationary solution gives me this. Log W bar minus C bar equal to 0, this. And so you can see my solution is this. So I have an optimal solution called long-run stationary equilibrium in this problem. You can see I didn't have to do too much work on this. I got it very quickly. So as long as you're not interested in transient, you have a solution very quickly, and you can sort of see that it's all the requirement of equilibrium. This is an interesting concept, and after this, I will take a break. So, golden path. In economics, you will see a concept of golden path. And the golden path concept says the following. It says that I will set x dot equal to 0. And this will give me a feedback control, ux. When I solve this, u becomes u of x, because this is the equation in x and u. And if I solve for u, it'll be ux, the solution. And then I can put the solution in the objective function. So the objective function will be phi x comma ux. Notice, if you look at this problem, if you look at this problem, if I set x not equal to 0, and I put phi of is x u sub x, and I integrate. Notice, this quantity is not a function of time anymore. So it can come out. If it can come out, integral of this side is then 1 divided by rho. And so I have a 1 by rho times 5xu. And so 5xu can be optimized without the integral. And that will optimize the integral as well, right? That's the only way. So I basically take the derivative of this 5xu with respect to x, and I solve for x. That is called the golden path. The golden path is that value of initial value of x that gives me an optimal solution over the values of x. That means given a number of initial values of x, what is the best initial value for which I can have a constant consumption or constant control all the way to infinity? So it is picking up the initial condition that is best for you. It is not optimal long-run stationary equilibrium, because optimal long-run stationary equilibrium, for example, may allow you to not keep the wealth constant, right? Wealth is not constant here as well, for example. So the optimal long-run stationary equilibrium is an optimal solution given any initial condition. Golden path, on the other hand, is an optimal solution over the initial values, which is the best initial x. So here's a thing. Suppose you wanted to find out what value of optimal initial value that you would want. So you say, oh God, give me an initial x. And obviously, you wouldn't want the God to give you a golden path initial value x. However, once you got your golden path initial value x, and if you want to optimize that solution for yourself, you will find that it may not be that solution, which is using the constant consumption, because you would want optimal long-run stationary equilibrium, and that may actually change the way you have your initial value x. So there's two different concepts, okay? Golden path, but they are, however, connected in some way, in the sense that if if your discount rate is 0, then and if you can make sense of the optimal solution in some way, then solving the optimal control problem and solving the golden path may give you the same solution. We'll talk more about it later. And then this is basically just a table that gives you different kind of objective function and state equation and current value function. And it kind of characterizes some of the solutions, some given name for these solutions. But we have done all of that, and given every kind of problem, you can do that. At one time, we had a whole chapter on this book, but we decided it's not interesting to have the whole chapter on this. So there are the different model types. Linear quadratic case is one of the most important cases in control theory. If I have absolute value somewhere, then it's not differentiable at 0. But I can change this problem into u1 plus u2. And then I have a u equal to u1 minus u2 and u1. So I change u to u1 minus u2, u1 bigger than 0, u2 bigger than 0. Then I can write this as u1 plus u2 provided this condition is satisfied. So I have a nonlinear problem. That means I can convert a non-differentiable problem into a differential nonlinear problem. And so at least I can handle that in a controlled way. But you will see in chapter 5 that I don't need this condition in many cases. So by doing this, I have a pretty simple problem. It's no longer a nonlinear constraint like this, which is difficult to deal with. Okay, so I think that one, if I have a bang control, but multiple vector control problem, then this bang control may not be like go from -1 to +1 because I now have many different values. And what it means is that if you have that, then you have a linear programming problem. So if you maximize the Hamiltonian at each point in time, the Hamiltonian is exactly this. So this is nothing but a linear programming problem. Maximize CU and AU bigger than or equal to 0 is a linear programming problem. So the bang solution means in a linear programming problem, this constraint is what's called a simplex. And the simplex is like this. And your solution goes from one corner point to another corner point to another corner point to another corner point. And so that the bang solution in fact becomes that kind of a solution. And we will see an example of this in chapters 5. In the finance chapter, we'll see an example of this. A remark about salvage value. Well, if T is free, the salvage value makes sense only in two cases. Either T is free, and part of the problem is to determine optimal T. So that makes sense. Or T is fixed, but the optimal value is no longer determine T, but the salvage value still makes sense. But if T is fixed, you can remove this T from the salvage value. So the function is like this. But in order for us to become a uniform notation, I have started right from the beginning, even though T is fixed, I have given this formulation. And the reason I've given this formulation is to also cover the case 1, okay, where this T makes sense. But it only makes sense in these two cases. Otherwise, you don't need a salvage value altogether because then T is fixed and XT is fixed. The salvage value when XT is fixed is not necessary. There's something called impulse control, which is basically a theory that was developed by our main Ben Susan and his advisor Lyons in 1975. The impulse control means that you have infinite control at very instantaneously, okay? And that control means that's called impulse control, and we don't cover impulse control. There are examples where we have infinite control at one instant, but we can handle that basically using a limiting procedure with the standard control theory problems. And so we never go into impulse control, but there are papers that Ben Susan and I have written using impulse control in our field, and they are available. So anyway, this is finish at chapter 3. We'll go to chapter 4. Let me just 10-minute break, and I will go to chapter 4. Let me put up chapter 4 here in the beginning. Okay, so this is where. Okay, let's take a break. Okay, everyone back? Okay, I'm
Yes,
with-
Professor.
Yes, yes, Professor.
Okay.
Yes, Professor.
Okay, the screen is still there, available? You can see the screen?
Yes.
Yes.
Yes, we
yes,
can.
yes.
Yeah.
Okay, so as I mentioned to you, chapter 4, with pure state constraints, is one of the most difficult problem in control theory. Now, since we are not doing the proofs, we will give you the maximum principle. Their proofs are obviously more complicated than the previous chapters. And the solution of the problems, even using those maximum principle, is not that straightforward. So the problems are difficult to solve, but the necessary conditions are there. And whatever they are worth, in some cases we can use them to solve it. In other cases, we have to design numerical methods to solve the problems. And so with that kind of remark, let's begin. The completely different structure of presenting this material than I did in 1983 when I wrote this book, the first edition of the book. Okay, let's take this problem of maximizing from zero. By the way, have you read this chapter before coming here? Anyone who ever read the chapter?
Yes, some parts, not all of that.
Yeah, it is. Once again, I cannot overemphasize the value of reading the chapter before the lecture, because you will get more out of it, and it is, as a PhD student, you want to learn the topic rather than just work on minimal amount to pass the test. So 0, 3 minus u dt, x dot equal to u, x0 equal to 0. Control is restricted between 0, 3, but we have a state constraint. You see, there's no control here. And given this, that we are maximizing the minus u dt, which means we are minimizing u dt, which means you want low values of control. So this problem has a state constraint, but as long as we can guarantee the low values of control, then we know we have solved the problem. And in solving the problem, we'll discover some aspects of the problem that will let us know that the problem of generalizing this problem and finding the maximum principle is tricky. Okay, so this is the purpose of this exercise, is to give you a deceptively simple exercise, yet the exercise reveals certain things about necessary conditions that we must have, and the maximum principle that we will need to derive, or we need to have. Okay, so here's the problem. This parabola that you see is this constraint in xt space. So this is x, this is t. This is a parabola, and it says that I must have x above the parabola. Notice that if you are at a parabola point, wherever you are, let's say here, if you're at this point, then some control are not feasible because you will go in below the parabola. And the some controls are feasible because they are above the parabola. But we need to maintain x. The only way to maintain x so it doesn't go above or it doesn't go below the parabola is to control x dot. See, if a constraint is on u, control variable, then we can just use the constraint to find the control that satisfies the constraint. But now we have to use the control to satisfy x constraint. Well, we cannot change x without using control. So the only way to satisfy the x constraint is to control x dot via u. So for example, if you are x dot here, you don't want x dot so that x will go below a parabola. So you need to restrict x dot so that x stays above the parabola. So the constraint is, even though the constraint is on x, it implies a constraint on x dot. Because it's only via x dot that you can control u so that you can control x dot. You see the difficulty here? The difficulty is one level removed. I cannot manage u by itself using the constraint on u. I have to manage x by using the manipulation or regulation of x dot. And x dot is given in terms of u, so I have to change and manipulate u to manipulate x dot to keep x in line. Now, it is possible that x dot is, it is possible that x dot is, doesn't have u in there. Like remember in the example of the train example in chapter 3, x dot was y and y dot was u. And y is not a control variable, only u is a control variable. X dot equal to y is not a control variable. So if x dot is not a function of u, then to regulate x, you have to regulate x double dot, because only x double dot has a u. Because x dot doesn't have a u. So let's right away say the following, that if x double dot has a u, but x double dot doesn't, then this is called the second order problem, because I have to go to x double dot to manage x. If I have to go all the way to x triple dot to manage x, then it's called a third order problem. We will not deal with the second, third, fourth, fifth order problems. You can have a theory for that, and there is available literature. In this chapter, we will only deal with the first order problem. First order problem means x dot itself has a u in it. Okay, so we don't have to go to the next order, because then maximum principle becomes more complicated, and one can write it, but I think that means I'm going to write quite a few pages of the maximum principle and have a very few problems on which to apply. Most problems in our field has an x dot which itself has a control in it. Okay, like the wealth consumption, right? You change wealth by consuming, so you don't really have to go to the second level. But in the train example, you go to second level because it's a technical example where the force gives you acceleration. Acceleration is x double dot. Not in our field, not on our field. So we will only deal with first order constraint. This is a first order constraint because x dot is u. There's a remark somewhere to this effect, but I want to do this right away. So how do we solve this problem? Well, look at this way. If I begin with 0 and I want minimum control, and the minimum control is 0, so I can use 0 all the way up to here. Up to 1 time 1, I can use control 0. And after 1, if I use control 0, I will go below the parabola. So I need to use that control that keeps me right the parabola. Any other control that will go up the parabola will be bigger control than the one that goes along the parabola. So hopefully after this, I can find a control that goes along the parabola, and that would be part of the minimum control and hopefully part of the optimal solution. Then when I reach 2 times 2, x is 1, I'm at the top of the parabola. If I use the control to go along the parabola, I need negative control, which is not allowed. So I cannot go negative control, which is not allowed. Going above will increase the value of the control and decrease the objective function. So from this point on, I can again use 0 control and go all the way to 3. So you can sort of see that the optimal path in this problem is a path that goes from here to here, goes from here to here, here to here. And for that, I can find control easily. Okay, so let's do that. So I already told you all of that part. But at t equal to 1, I need to make sure that the control goes in such a way that I will ride along the curve. Well, how do I do that? Well, first of all, I want this x dot, just take the derivative of this with respect to time and set it bigger than or equal to 0. So the x dot will become u, then there's a control coming from t. So the derivative of that will be exactly this. And that must be non-negative. But if I use exactly this control, then this will be 0. This quantity will be 0. The derivative of this quantity will be 0. And that would allow me to basically ride along that curve. So I will set ut equal to 2 times 2 minus t. ut 2 minus t will give me all the way up to here. And then at 2, remember this control has already become 0 because this is a tangent here. And so it becomes 0. And then I will just keep it 0. I cannot go below because 2 minus t, when t equal to 2, t is bigger than 2, this becomes negative. So to go along the curve require negative control, which is not allowed. So I put ut equal to 0. So I have the following solution. X star t is 0, x star t is the parabola, x star t is 2, 3 is basically 1 because the control here, the x remains 1 and control is 0. And here the control is 0 up to 0, 1 and xt is 0, it remains 0. Here control is 2, 2 minus t, which allows me to have x star t along the curve. And I keep it 0, which allows me to keep the 1 at constant. So now what I want to do to show you that if I use this solution to compute the value function, it is intuitively obvious that this control is optimal. Of course, we will eventually show that it satisfies the maximum principle, which has been proved by some people in literature, and it will verify our conjecture that this satisfies the necessary condition and hopefully also sufficiently conditions and such an optimal control. But it doesn't require much because you can easily show that there's no, you cannot do better. So let's do VXT. Now, the only thing I want to mention to you, and I think this requires another little, maybe one change. It's not a mistake, but maybe just like I previously, you can improve the exposition a little bit. Maybe I will do that. I will show you what I mean by that. In order for us to find VXT, we need to have x and t arbitrary. So for any x condition given at time t, not at time 0, at time t, because we need VXT, we need to be able to find the optimal control from any given xt. For any given xt initial condition, we need to find the optimal control. And the optimal control is more or less very simple here. If you are here, you go up to there, and you ride along the curve and go like this. If you are here, you just go like this, 0 all the way up to 3. So that's the optimal control. If you are here, you go all the way up to here, which is more than 1, and then you ride along this and go there. So you can do that. Xt here is not allowed because it's not feasible. Let me tell you what else is not allowed. If I use sufficiently low control, low x, then I can do this 0 business here. See, I can do this 0 business from here to here. But then I come to a point which is so steep that to ride along that will violate this constraint 3. That means I would need a control u, which is bigger than 3. So no feasible solution from there. So Vxt is minus infinity for those x. So I need to identify all of those xt for which the Vxt is minus infinity and take xt, which is feasible, from there, find the optimal control and then compute the Vxt. Notice now the optimal control from there to there and it is infeasible is a little bit difficult. And the reason it is difficult is because if I go this far, I can't go back. If I go this far, I'm already sunk. This is another reason why these problems are difficult, because you need to think about future as to what might happen that does not allow you to proceed further. And if you were to do that, then you have to, maximum principle has to tell you somehow that that's not allowed, okay? So what is allowed? Well, it's clear what is allowed. Can anybody tell me what I should do? If I'm here and this slope is bigger than 3, and the slope is bigger than 3, can easily find out. See, this means this is bigger than 3, and you can find out, what the values of the x would be. Okay, given that we have short time right now, if I'm there at such a point, then the optimal control would be to go like this and land at a point on parabola so that the slope is exactly equal to 3. And then just go along that, because the slope is decreasing. As I go along, the slope is decreasing. You see that? And so if I land at 3, then the slope will go from 3 to 0. But I don't want to land at a slope when the slope is 4. Okay? So x dot, which is given by x dot, which is given by u, and the x dot for this one, you can easily find out that slope. And this is 2 minus t, and you make this bigger than equal to 3, you will find out where that t is, and then you can find out the x value of it. I have done that. And so I'm not allowed. So there is x01, that's fine. But if I take any t, then I need to also make sure what what X values that I'm allowed. So the control is 0 until hits the trajectory at time tau, which is 2 square root of 1 minus X. So from any given X, which is feasible, and so let's take a xt here, for example. Then from there xt, I will go here. I need to find out how much time to, how much, I don't want to change the picture, but obviously if I don't save it, it will be okay. So I have to find out this time t, and then find the slope and go along like this, okay? In order for me to do that, you take from X, the control is 0 until this time tau, which is in terms of X. Then the control switches to 2 times 2 minus S from tau to 2, and then climb along the left-hand side to each peak, and then switches back to 0. So for that, I can find the value function. So the value function xt is from t to tau, which is this tau, is 0 control. Then from tau to 2, it is 2 times 2 minus S, just this formula. We have 2 times 2 minus t, that formula for S. And then from 2 to 3, it is 0 again. So this is 0, this is 0. I'm left with this guy. I can integrate that very easily. And I get Vxt equal to x minus 1. And we have the value function Vxt equal to 0, x bigger than 1, because x bigger than 1, I will have only 0 control all the way. And so Vxt is 0, because 0, u will be 0, the integral will be 0, so this is that. For Vxt, x bigger than this quantity. So what I've done is to make my life simple. I have choose x so that this kind of control is optimal. I didn't use a control so that from x, I need to go, I don't know how I cannot do that. I need to go like this and then land somewhere here, like that, and then go here and then right along that. That will have a different formula. But it can be done, and I did not do it because it requires some amount of work, and then it is maybe not necessary for this example. What I want to say is something simple, and that's what I'm going to show you right now. So for that kind of control, where this control is optimal, this kind of control is optimal, I find the Vxt, and I can choose the values of x for this kind of control to be optimal. If I go to other values of x that are still feasible, then I need to, for those xt, I need to find a different control and different Vxt. And that would require a little bit more calculation. It can be done, but so I have this control. Now let's take V sub x. Take V sub x. That is 0, so it's no problem. That is 0, is no problem. But take the V sub x here. That V sub x is 1 from 0 to 2. And it is from 0 from t equal to 2 to 3. Because I take the V sub x and put extra t in there. Because remember, lambda is the V sub x on the optimal path. So if I take V sub x, which is exactly, if I take the V sub x, then, and put the value x star t, then what happens is it is 1 from t0 to 2, because this is 1, we take the V sub x, it's 1. But from 2 to 3, it is 0. So in particular, at this particular point, exactly at this point, at the peak, you see on the left-hand side, the control has a different structure. The right-hand side has a different structure in some sense. It's continuous, but the control, the value function is not continuous. If you see value function exactly at 2, on the left side it is 1, and the right side it is 0. Did you get that? So for my exercise, I didn't really need to go to points that are far below, and I need different kind of control. That would be an exercise to find Vxt, yes, but it will not be an exercise to demonstrate that that value function has a discontinuous derivative at this point. But those points will only make my life complicated, but in the end, I'm only trying to find out the discontinuity at this point. But if that was lambda, then lambda at 2 will have different value on left hand side and a different value on the right hand side of 2. That means the lambda itself will be discontinuous. And it will have a downward jump of the size of 1 at time 2. So what I'm trying to say is that we have lambda dot, and lambda dot is a differential equation. And any integration of a differential equation will give you a continuous lambda. So our maximum principle with the lambda dot equation cannot be generalized anymore because I need to allow a discontinuous lambda. Remember, this is the lambda. And even this example, I cannot have a continuous lambda. And so I need to have a discontinuous lambda, which means the maximum principle must allow discontinuity in lambda at these kind of points. At the points where the state constraints are active. Okay, these are maybe this point, maybe this point. There may be a possibility of lambda being discontinuous. And that's why the problem becomes difficult. Think of 2-point boundary value problem. 2-point boundary value problem solves the problem x dot lambda dot this way. But if lambda was discontinuous at some point, how am I going to do the 2-point boundary value problem? Because I need to allow for discontinuity in lambda. And then I cannot connect the terminal value to the initial value anymore because there's a jump in between. So this example basically gives you a difficulty. This example comes from my survey of state constraint optimal control problem, which is a huge survey that was published in Siam Journal of Control. And it's a popular survey because state constraints are interesting problems for management science, but they are also difficult. And the literature is vast, huge amount of literature on state constraint problem. There may be 1,000 papers. And anyway, so the survey was done at some time ago, but perhaps one could do another survey and look at the literature since then, but who has the time? Not me. Okay. So let's now put that discontinuity in the maximum principle and give you the maximum principle. Again, we are not going to prove it, but we have given you a reason why I need to modify the maximum principle. So start generally. This is the kind of constraint that we want to impose. This is the constraint, that generalization of this constraint. This is the constraint whose generalization is hxt bigger than or equal to 0. So here's our constraint. And then you can put, some conditions on this function, which is a vector. So this is standard, okay? I already gave you what rth order means. Rth order is when you take r derivatives before you see a u term on the right hand side. So we'll only deal with first order constraint. So first order constraint means r equal to 1. And when I take the derivative of this constraint h sub 1, which I will call h1, which is dh dt, which is a total derivative. Total derivative will be delta H delta X times F plus delta H times delta T. And I want that derivative to have a term in U. It cannot be without U, okay? like the train example. You will have a Y in the train example. So each of these constraints, H sub I, would have to be first order constraint. In our field, we don't see this kind of constraint. Sometimes you can, but it is not usual. Usual constraint is this kind. Non-negative constraints on wealth, inventory, advertising, goodwill, whatever. Sorry. And for that constraint, H1 is simply F, because H1 is X dot, and X dot is just F. We can also have constraints of this kind in our literature, where Xt is less than or equal to M. But in that case, H1 is minus F. But that's general, okay? That allows this. Well, there is some terminology. The horizon is 0 to T, and pick up 2 points. So there's an interval which is a which is the subset of this 0T. This is called an interior interval if HIXT is strictly bigger than 0 on theta 1, theta 2. So go back to our example. If I took theta 1, here and theta 2 here, you can see this is interior. Interior means inside the constraint. Outside the constraint is feasible. With inside the interior means constraints are satisfied, more than satisfied. They are in the exactly interior. So this is the interior of the constraint. This is the exterior of the constraint. This is infeasible part. So any 2 points of time which is in this interior is called the interior. This segment is the interior segment. Here the constraint is not applicable at all. You don't, because it's strictly inside the boundary, then the constraint is not active. Okay. This is if I take theta 1 here and theta 2 here, which means the x is along the constraint. This is the boundary interval. Okay, so this is let us see the terminology here. Hits the boundary. So if the optimal trajectory hits the boundary, that means satisfies this at tau 1, t, tau 2 for some I, then tau 1, tau 2 called a boundary interval. And in this case, tau 1 is called the entry time if an interior interval ends at t equal to tau 1. So this is the entry to the constraint. And a boundary interval starting at tau 2 is called the exit time if the boundary interval ends at an interior constraint. So go back to the example. This is an interior. Okay, interior allows you, go back to it again. Interior says that this is strictly bigger than 0. So the interior will be somewhere here, but not. Now this is the boundary interval. This one is a boundary interval, and this is the interior point because I'm entering the constraint. And here I'm what am I doing here? Yeah, I'm entering the constraint. And if I leave that, I will go unfeasible. Here I'm leaving the constraint. I was on the boundary and I'm going back in the interior. So I'm leaving the constraint. I cannot leave the constraint going the other side. I can only leave the constraint going into the interior. Okay. So this is the exit point. This is the entry point of this particular boundary interval. So this, if this is theta 1, this is theta 2, this will be a boundary interval, and this will be the entry time, this is the exit time. If it starts from here, then there is no entry time because it's already in there. So these are some of the terminology, because if you go beyond what I'm saying, then maximum principle can give you more information depending on the type of interval that we are. Okay, and we're not going to do too much on it, but if you have a problem that requires optimal control, then you may need this kind of terminology. If it touches the boundary and leaves immediately, so you can have a control where you can go like this. You go like this and then go like this. So you just touch the point and then leave again. That is called a junction point. Let me see where it is. This is the time tau is called the contact time, and taken together, the entry, exit, and contact times are junction times. So there's a contact time, then there's entry time, exit time, and they're called junction times. So these are all the terminology, okay? I mentioned to you, I may not cover that material, but in chapter 11, I give you mechanism design when the types are continuous, not high and low, or high low means more efficient and less efficient, and only two types. Most of our literature on mechanism design basically has two types, but there's a literature on continuum of types. And if the types are continuum, then that literature requires control theory. And I have given a whole long section on mechanism design with continuum of types. And if anybody is interested in working on mechanism design with continuum of types, would require to learn that theory. Although I would not cover that because I won't have time. It's somewhat complicated because you need to learn mechanism design before I can even introduce that material to you. And three, I don't have the slides yet because this chapter was written before the slides were generated, and I'm right now out of a secretary. So I don't have any way to do the slides. I have very little skill on doing slides and using computer in some way. Okay, full rank condition on boundary interval. Again, these rank conditions are something that we put in so that there is an existence of a solution, but I would rather not spend time right now on it. If you have questions on this, you can ask me later. So let's move on and go to the problem. So this is our problem in chapter 4. We have an objective function like before. We have a x dot equal to f. We have a g xu2. This is a mixed type constraint, chapter 3. Sxt bigger than 0. This is current chapter 4. And we also have a constraints on the terminal condition, which are also expressed as inequality. See, this would be more like a fixed endpoint, right? Xt equal to 5 would be part of this constraint. Wt bigger than or equal to 0, which is the wealth condition, you don't want to go bankrupt, will be a condition of this type. But in general, there could be functions on these, and you can have this kind of conditions. So the ones that we have dealt with would be special cases of these. what we want is a maximum principle for this problem. Special cases are already given. We already talked about it. These are special cases of these kind of constraints. Okay. So there's another problem. The problem is that there are two types of maximum principle in the literature. I like the indirect method, so my first two editions of the book only have indirect method. But the sufficiency conditions are only there for direct method, although you can use indirect method by equivalence between the two methods. But literature has both, and so I cover both methods now in this book. Most of the examples that we will solve beyond this chapter 4 will use indirect method. But it's better to begin the theory with the direct method. I'll tell you what I mean by that. So D is for direct. Direct Hamiltonian is exactly the Hamiltonian we are used to. And the Lagrangian is exactly the Lagrangian up to this point. And then I have another Lagrange multiplier for the state constraint. You can see this is, again, just like this, I use this. I don't put D on mu because we will find that when we do the indirect method, that mu will be the same. But lambda will be different, eta will be different. So I don't put X and U should be the same because optimal control should be the same. But lambda and eta will be different in the two formulations, although there's a transformation that you can do. But I put the superscript. So the maximum principle now is there exists all these multipliers such that X star satisfies this equation. It's a dot here, you see. Constraints are satisfied, both mixed and pure. Terminal conditions are satisfied. Lambda dot D, which is the derivative of the Lagrangian, is satisfied. Transversality conditions. Now notice the transversality conditions. Up to here we already know. And then I need to put T minus. That means the conditions are just before T. Because at T, there may be a discontinuity. So I need to put T minus. Lambda D at T is absolutely known to us. Lambda D at T will exactly will be the derivative of S with respect to X. Because that is marginal value. If you're already at T, that is your marginal value. But what if there's a jump in lambda there at that point? So before T, is doing whatever it's doing. For example, if the T was like this, if T was, if I gave you capital T exactly 2, if I gave you capital 2 exactly at 2, then exactly at 2, the lambda will be 0 because there is no salvage value in this. But before 2, we already found out the lambda is going to be 1. I mean, because V sub x is 1. So you can see V sub x would be 1. So Vx1 has to be at T minus. That means at 2 minus. At 2 minus, it has to be 1, and then it is 0 at 2. Okay, so that's why I need T minus. T minus is connected to the problem. T is all by itself separate. If it's the same, fine. If it is not the same, well, I cannot do anything about it. So we already know lambda dt by definition, which is the same throughout the book. But at T minus is the condition. Transversality condition at T minus, not at T. And then we have complementary slackness condition, and then there's a new condition with gamma, which is with the X. So there's another complementary slackness condition. Maximizing condition is the same as before. But now I need a jump condition. at any time tau, where lambda d is discontinuous, then time at tau minus and time at tau plus, the jump has to be of this size. So there's another variable coming, zeta d. So you can see there's a zeta d in writing the maximum principle. Zeta d here, you see jump parameter zeta d. That is a jump parameter at time tau that has to satisfy this. And the Hamiltonian at that time tau has to have some kind of equality, and there is some kind of a jump. And that jump will be 0 for, see, this ht equal to 0. So if the constraints are of this kind and not more complicated kind, then h sub t will be 0. In all of these cases, the Hamiltonian will be continuous at the jump point, because this will be 0. But if this is not 0, if h sub t has a derivative with respect to time, if this has a derivative with respect to time, then that derivative has to influence also the jump in the Hamiltonian. This is similar as before. And these are all complementary slackness condition. You have one extra condition because of eta and another condition because of zeta. So it is substantial. But that is the necessary condition. Why I don't use this and not go further on this is because lambda d is not only discontinuous, but it is a more continuous, more complicated function. It's a more complicated function because it can be what is called a generalized function. That means it can be more complicated in the sense that at some point it can have an infinite value of some sort. So it is more like a generalized function. And so that requires even more sophisticated mathematical concepts. But so I don't go much detail into lambda dt, but you can see lambda dt at capital T is exactly this. And then you can also write, if T is free, you can also write a condition for T to be optimal, T star to be optimal. And you can see there's an extra condition coming in there for the alpha type of constraints. And there is a gamma constraints coming in there. So it is, again, a whole lot more complicated. So now try to get the J star T to be optimal. It requires quite a bit of extra work. Of course, there's a Hamiltonian, so you can still use the proof that I had. I'm again going to skip those. We are writing this for completeness of the book, but we are, if you write a paper, you may have to verify them. But otherwise, we needed to verify some of these things. We just wrote a paper on pandemic control, which just got accepted in PALM maybe about 2 months ago. It might have already appeared. Yeah, it's already appeared in the online version of PALM. So that's another maximum principle application that we did for the pandemic problem.
Professor, I guess we run out of time.
Oh yeah, we are out of time. Okay, so what we will do, we'll continue with chapter 4. The homework, let me give you the homework. We are because, let me see, because we decided to do a lot of homework design before the semester started, partly because my secretary left, and we decided that we will, but so sometimes the homework maybe like last time was a little bit out of sync because we are a little bit slower in covering the material, which I don't mind at all, because whatever we learn, Um, if I can give you more insight into what is going on, that's good for us. And at least you learn better what we cover instead of the other. So the homework is going to be, even though I didn't cover the material, chapter 4, I will actually give you the homework, which is due. Oh, by the way, Gautam, are you there?
Yes, Professor. Yes.
So what was the homework last time? Was it 4.13, 4.20, 5.12?
Yes, Professor. I assume so. Let me
And
see.
that's due next week. There's no homework due this week, right?
Yes, Professor.
Right. So the homework that's due next week is already given to them, right?
Yes, Professor. I sent an email
Okay,
last
so we
week.
don't give any homework today.
Yeah.
Okay, good. So we give one less homework because we are a little bit out of sync. So the homework is going to be due next week, even though we did not cover some of the chapter 4, but I don't want to go and give you one more week and skip 2 homeworks. So please read the chapter and do the homework. And it's probably a good idea anyway, because I ask questions. If you slow me down, we may have to skip one more homework later. Okay, so the homework is two problems for chapter 4, one from chapter 5. Next week's homework will have 2 chapters from 5 and 1 from chapter 6. But I will give that to you next week. Okay? Thank you.
Thank you, Professor. You have a good day.
Yeah.
Thank
Bye
you,
now.
Professor.